Okay, so what we're going to do is we're going to talk about work and energy. And so in this unit, we'll talk about work done by a constant force. We'll discuss work done by a variable force, work energy theorem, which is the difference in kinetic energy, and potential energy, and the conservation of energy, and power. So the first thing is work done by a constant force. So if the force is constant, in other words, the force doesn't change, it's a constant acceleration of a mass. Well, then the work is equal to that force times the displacement of the object, so long as the force is parallel to the displacement. So here we have a couple of examples. In example number one, what we have is we have a gentleman applying a force to an object, but for whatever reason the object is not moving, so the displacement is zero. No work is being done in example number A. In example B, what we see is the force that's a pull, right? Remember, a force is a push or a pull. So we have a pull that is parallel to the displacement. So work is being done in example B. Now in example C, this young lady is pushing on a lawnmower, but she's pushing at an angle. So if you take the components of the force vector and divide it in or split it up into the vertical and horizontal component, we notice that the horizontal component is parallel to the displacement of the lawnmower. So there we would calculate the force by the magnitude of the force times cosine of theta. And so if the force is at an angle to the displacement, the more general form of the work is calculated by force parallel to displacement, or in the case of this lawnmower, force times the cosine of theta, d. Now the unit of work is Newton meters, and we call that joule. Work done by a constant force is very similar to motion and velocity and acceleration. And so if the force is going in the same direction of the displacement, then the work that's done is positive. However, we do have a scenario like down here at the bottom where you can have a force that's going in the opposite direction of the displacement, which is like a car and you're slamming on the brakes. And just think about that. If the velocity is slowing down, the car is still moving forward or still being displaced in a forward motion. However, you could have something pulling against it. So a better example of this is somebody falling from an airplane. They're being displaced, but when they open the chute, the force is pulling them backwards, but they're still being displaced in the forward direction. So then what we need to remember is that work is done by a force, and the force has to be parallel to the displacement. So as we look at this object here, according to the free body diagram, there's a whole bunch of forces that are taking place for this little object in motion. Well, the displacement can be measured from here to here, so then what I need to figure out is the net force parallel to the XY plane, right? So we have a block, it looks like it starts at the top of this inclined plane and slides down. Now, truth be told, I could mathematically figure out the force that's being applied parallel to this displacement, but that's not really how far the object's being displaced, right? The object's being displaced from here to here. Okay, so that's how we would calculate that. Now, a variable force is a force that changes at a constant rate sometimes, or sometimes not at a constant rate. So we're going to focus on a change at a constant rate of change. And so the force exerted by a spring is, it varies linearly with the displacement. In other words, the further I pull the spring back, the more force the spring applies to an object wanting to go in the opposite direction, which is why the spring force, or F sub S, is equal to the negative K, which is the constant of the spring, which is just a number that we use that's calculated based on the stiffness of the spring for the most part, times the displacement K. So again, we're going to have a displacement times a constant K. Well, remember that work is equal to the force times the displacement, and the displacement on a spring or a variable force is kx, or negative kx. So when you apply the force or multiply force, which is kx, times the displacement, we see here that the slope K is the increase of the force. So in other words, what this graph is saying is the further I pull the object away from rest on a spring, the greater the corresponding force is. And the work that's done in that process is the shaded area under the curve. Well, how did they come up with that? Well, the net force acting on an object causes the object to accelerate because force is equal to mass times the acceleration. Well, acceleration, if you remember from kinematics, is actually the velocity squared, the final velocity squared, minus the initial velocity squared, all over 2 times that displacement. Well, if work is force times displacement, and force is mass times acceleration, but acceleration is v squared minus v naught squared over 2x times x, when we multiply this through, we get that work done is going to be equal to minus 1/2 mv squared minus 1/2 mv naught squared, which are the initial and final velocities. Well, that's the same formula for kinetic energy. So so the kinetic energy is equal to 1/2 times the mass times the velocity squared. Again, the SI unit for energy is joules, and the net work on an object is basically the difference in the kinetic energy. And so what we mean by this is if I have an object here and I apply a force, that force has an acceleration which causes the object to move. So we have an initial velocity here. So the initial kinetic energy is going to be 1/2 times the mass of the object times the velocity at the beginning squared. Well, that's the initial kinetic energy. Well, after some time, the object is displaced a certain distance. If the force is constant, then the acceleration remains the same. However, that acceleration could increase, or if it's a negative acceleration, decrease the velocity. So the final kinetic energy is 1/2 times the mass times the velocity squared. If we take the difference of those two kinetic energies, since it's being done over a distance or displacement, then we would say that the work is equal to the difference in kinetic energy. So potential energy may be thought of as like a stored energy, such as a compressed spring or an object really high above the ground. And so the work done also changes the potential energy. So just like work is equal to the difference in kinetic energy, it's the difference in potential energy. And so if we're thinking about a spring, basically to calculate the potential energy of a spring is 1/2 times the spring's constant K times the displacement squared. And so we have, again, of a final force and an initial force times a displacement. That's where we get the x squared from. And just like before, since potential energy is an energy, or in this case the energy of a spring, we denote that as the SI unit of joules, which is Newton meters. And so another type of potential energy is gravitational potential energy. And when you think about it, gravity kind of works like a spring, right? So when I lift the can up above the ground here, well, gravity is kind of pulling down like it's attached to a spring, but it's an invisible spring. And so as soon as I release the can, what the can will want to do is go back to rest. So we calculate that a little differently. But it's really the mass of the object times the acceleration due to gravity times the height, which is usually measured in the y direction. So we would say mgy. What's nice, though, in physics problems is that we can arbitrarily choose the 0 point. In other words, if I look at this object here on the second step, and I label the first step as y equals 0, then my total change in potential energy should be 2h. And the way that I get that calculation is if I go 1 unit y down, then my potential energy is equal to negative mgy because we go negative y. And then here, if I start at the top, my initial potential energy is just mgy. So we have mgy minus mgy, which is 2 mgy. However, if I allow the bottom floor over here, the green, if I start this as y sub 0 equals 0, and then I go from the top tier, my potential energy is 2 mg. My final energy, because y equals 0 is 0, then when I find the difference between the two, I have a potential energy, or a difference of potential energy, which is 2 mgy. Now remember that the difference in potential energy is actually the work that's been done on the object. Conservation of energy basically states that if we observe that all the forms of energy are accounted for, the total energy of an isolated system does not change. This is the law of conservation of energy. So the total energy of an isolated system is always conserved. We define a conservative force as a force said to be conservative if the work being done on it in moving an object is independent of the object's path. To continue along those paths, we say, so what types of forces are there? What is a conservative force? Well, a conservative force is gravity, because gravity acts on an object and causes the object to move. But it's not, the difference in the initial and final height, but it's not on the path between the two. Similarly, and this is the more important thing, remembering a conservative force is kind of a gray area. It's easier to remember what a non-conservative force is. So a force is said to be non-conservative if the work being done on it in moving an object does depend on the object's path. So the biggest non-conservative force that we talk about is friction. So conservative forces are kind of, we have a total system and the energy is transferred from kinetic to potential energy, but some of the energy is used up in friction and heat. The friction and heat that kind of appears to use up the energy is a non-conservative force because the heat and friction is based on the path of the object. So the conservation of energy of a system is basically the total mechanical energy, which is E, which should always equal the sum of the kinetic energy at that point in time and the potential energy in that point in time. And so the force is conservative if the work done on an object through a round trip is 0. So then if we're only dealing with conservative forces, then delta K plus delta U should be 0. In other words, the difference in kinetic energy plus the difference in potential energy should always equal 0. And so kinematic problems that we learned are so much easier to solve when we think in terms of energy. So if we look at this example here, we say that all three balls have a similar kinetic energy because they have an initial velocity. As the kinetic energy changes to potential energy, because the energy is conserved, it doesn't matter how the ball is elevated and at what angle, their speeds just before they hit bottom are all going to be the same. They'll land in different locations, but the energy is conserved. Well, let me back up there. I'm starting with an initial energy to the system. If, for example, this one goes up, as it goes up, the kinetic energy slows down, and right at the maximum height it has its maximum potential energy, and then it will fall. However, if I look at the path of the first ball, which is 45 degrees below the horizon, it has an initial velocity that's going in the same direction due to gravity. So because the energy is conserved, we have a kinetic energy plus the sum of the potential energy, and so the total mechanical energy, because there's no friction, at least we're neglecting air friction, the total kinetic energy at the bottom should be the same in the system when there's absolutely no potential energy. In other words, right as the ball hits the ground, the potential energy for all three are 0, and that should equal the initial kinetic energy plus the initial potential energy because the energy is conserved. Another way to look at this is to look at the conservation of energy as a ball hits a spring. So what I want to point out as we look at this diagram is this is the potential energy due to gravity. K stands for the kinetic energy, and this is the potential energy due to the spring. So at this point, the spring is at rest. However, the ball is elevated quite high, way above the 0 mark. So this looks like the 0 mark right here, this little tick, this line. So it has full potential energy until I release the ball, because gravity will accelerate the ball and transfer it to kinetic energy. So if I let go of the ball, what happens is over here in the next picture, the ball is in motion. So about half the potential energy gets converted completely into kinetic energy. Well, right here in this next slide, as the ball hits the spring, what happens is the kinetic energy is even lower because it's closer to zero, right? And the kinetic energy has increased, but we have no potential energy in the spring because it's just making contact with the spring. However, once the ball starts to compress the spring, what happens is, as the kinetic energy will start to lessen, the potential energy due to gravity is lessening because it's getting closer and closer to the 0 point, and then the potential energy in the spring increases. Once the ball has fully compressed the spring, at that instant in time, the velocity is 0, no kinetic energy. Its height is at 0, no potential energy due to gravity. So all the energy of the system is now stored in the potential energy of the spring. If you look here and you count all these blocks, there's 10 units of energy. If you count these blocks, there's 5 plus 5, which is 10. Here we have 4 plus 6, which is 10. Here we have 2 plus this is 10, and then here the energy is completely transferred to 10 units of spring potential energy. So if a non-conservative force or forces are present, then the work done by the net non-conservative force is equal to the change in the total mechanical energy. This is like if I slide a block on a surface that isn't frictionless, in other words, there's a frictional force, well, the block will eventually stop. And so when I find the difference in the initial energy and subtract it from the final energy, the difference in energy is the work that's been done by the non-conservative force, which would be like friction, okay? And so one thing that we want to do is we're always thinking about these changes over time because we live in time. So the average power of the total amount of work done divided by the time taken to do the work is the power, which is equal to the work divided by time. If the force is constant and parallel to the displacement, then what we have is the power, which is equal to the work divided by time. But remember that work done on an object is the force times the displacement. Well, we have Fd over t. If I pull the force out, then d over t, remember that displacement over time is really the velocity. So we can calculate power a lot of ways. We can calculate power by work divided by time. We can calculate power by force times displacement over time. We can calculate power by force times velocity. So one last thing that we want to talk about is the mechanical efficiency. So if I put a bunch of energy into a system and I only get a certain amount of work out, that's going to give me a percentage of efficiency because no energy transfer is 100% efficient. So I'm going to have friction, I'm going to have moving parts when you have mechanical energy or machines working. And so in any real system, in this universe at least, we're always going to have an energy efficiency of less than 100%. And so to give you an example of what I'm talking about, a compressor, an air compressor, is only about 85% efficient. In other words, I'm going to put 100 joules into this machine, and I'm only going to get out about 85 joules of work. Same with an electric motor. If I pump in 95 joules of energy, I'm only going to get out about 95 joules of work. Automobiles are about the same. Human muscle is technically not a machine, but in terms of work output, compared to energy input, I'm going to get about 25%. And here we see the steam locomotive is about 10% efficient. And so what does this mean? Well, in Chapter 5, we talked about work done by a constant force is the displacement times the component force in the direction of the displacement. Kinetic energy is the energy of motion. Work energy theorem, the net work done on an object is equal to the change in its kinetic energy. And the potential energy is the energy of position or its configuration. The total energy of the universe or of an isolated system is conserved. Now, I don't remember if I said this or not, but all energy that ever will be has already been created and it will never be destroyed. It can only be transferred. So then that's what we mean by all the total energy in the universe. All right. And so then the total mechanical energy is the sum of the kinetic and potential energy. It is conserved in a conservative system. However, the net work done by non-conservative forces is equal to the change in the total mechanical energy. Power is nothing more than the rate at which work is done over time. The total energy, I guess that's the end of the slide.